All right, let's go through activity 3. So in activity 3, what we're going to be doing is understanding how to analyze the association between two quantitative variables, two variables that are numerical, using either the Pearson's correlation coefficient or Spearman's rank correlation coefficient. So like always, we want to read in library reg class so that all the datasets and commands are available to us. And question 1 deals with looking at the data frame called Survey 10, which is a little bit old of a data set now, but it deals with Stat 201 students from 2010 and questions they answered. So the first thing that we want to do is make the data available to us, and in this case it lives inside package reg class, so we can load it up just by doing data survey 10. We see that it exists now in the environment. And we're first asked to run the command core matrix. Now what core matrix does is it looks at all of the columns inside your data frame and then reports the pairwise correlations between each of the quantitative variables. So we see actually there's a lot of different variables in here, and so I say to use core matrix just on the first 7 columns of the data frame. If I did it on the entirety of the data frame, you'll notice how much output there is, too much stuff to look through. So if I just want to get the correlations between the first 7 columns, I can always refer to the columns of a data frame by putting in square brackets and then putting in 2 numbers here. The number before the comma gives me the row numbers that I'm interested in looking at, and in this case, since I want all the rows, I'm going to leave that blank. And the number after the comma tells me what columns I'm going to be looking at. Now I want the first 7 columns, so the numbers 1, 2, 3, 4, 5, 6, 7, and a shortcut for writing that sequence is just 1:7 here. Alright, so I'm going to delete these comments and run this. And we have fewer than 7 variables because one of the variables in the first 7 columns was categorical, and correlations can only be calculated with numerical variables. And so we have the results here. So along the diagonal we have 1s because obviously weight is perfectly correlated with weight. They're the same quantity. We have a correlation between height and weight of 0.6, and so we could easily scan through and just look to see what the pairwise correlations are. Now, the correlation between x and y is the same as the correlation between y and x, and so this matrix here is symmetric across the diagonal. The numbers up to the right match up with the numbers down and to the left here. All right, so we got that done. Part B asks us to run the command all.correlations. Now, all.correlations pretty much gives the same output as core matrix, just in a different form, as a list of all the pairwise correlations instead of a matrix. So the way that we do all correlations is by typing in the name of the data frame that we're looking at. And it has a bunch of optional arguments. You see that we can say what type of correlation we're looking at, Pearson's correlation or Spearman's rank correlation, put Spearman in quotes. Interest equals, and if we wanted to just look at the correlations with one particular variable, we would put the variable's name in double quotes. And by default, it's not going to sort this list, but we could do sorted equals significance in quotes or strength in quotes to sort that list. All right, and that's actually what we're going to do here, is we're going to sort all those pairwise correlations by their strength. So I'm going to add in sorted equals strength. And what this will do is it will list all the pairs of variables and all the pairwise correlations from the most negative, which is up at the top, to most positive, which is down at the bottom. Now we know correlations are stronger the farther they are away from 0, so values at the very top of this list and at the very bottom of this list represent the strongest correlations here. So we're asked what pair of quantities has the strongest positive, strongest negative, and strongest overall relationship. Well, let's start out with negative. Most negative is the correlation between desired weight and the number of body piercings, interestingly enough, with a correlation of minus 0.6. The most positive is the correlation between someone's weight and their desired weight. That makes sense. Hopefully people weigh about as much as they would like, so the two should be strongly related. Now, which is the overall strongest relationship? Well, that's the one that's going to be farthest from 0. The correlation between weight and desired weight is 0.87 compared to the minus about 0.6 or so for desired weight and number of body piercings. So since the correlation between weight and desired weight is farther from 0, it is the overall strongest relationship. Okay, part C asks us to narrow our search here and just to look at the correlations involving the college GPA. So I'm just going to copy and paste the command that we just ran because I'm going to add in the argument interest equals, and then in double quotes, the name of the variable that I'm interested in, the one that I'm just going to be looking at correlations with. Okay, so which quantity has the strongest correlation with GPA? It's either going to be at the top of the list or at the bottom of the list. And we see that the correlation between weight and GPA has a correlation of -0.2, and that's actually farther from 0 than the most positive correlation with the variable percent more intelligent than, the percentage of people's fellow students they felt they were smarter than. So the most correlated variable is weight, interestingly enough. All right, so the analysis we've done so far assumed that Pearson's correlation coefficient was the appropriate way to measure the strength of these relationships. And so by default, the all correlations core matrix are always going to report Pearson's correlation. Now, that's not always the case. We need a special shape for the scatter plot in the stream of points to actually use Pearson's correlation to summarize the strength here. So what are those conditions? Well, when we make the scatter plot, they need to look pretty much like an ellipse. The point cloud can't really have any extreme outliers. We can't have heteroscedasticity. So for instance, if I plotted the relationship between GPA and weight, we can just get an idea for, all right, was this appropriate? And well, it's kind of iffy. So the vast majority of points kind of look like they have this rough elliptical shape. But we do have these kind of outliers down here with GPAs of 0. These actually correspond to the first semester freshmen that don't have a GPA yet that we're instructed to put in 0 here. So there are a few small issues with using Pearson's correlation here. So, all right, we could try out Spearman's rank correlation instead, which we can use to measure the strength as long as we don't have non-monotonic relationships, something that has both positive and negative parts, some sort of curvature like a U shape. All right, so we're going to run all correlations on the same command from part B, but instead of looking at Pearson's correlation, we're going to look at Spearman's rank correlation. So I'm going to add in the argument type equals Spearman and run this again. Now this is going to output a bunch of warnings. We can ignore these. It's just a warning that says that, hey, you have some ties in your data. Spearman's rank correlation looks at the ranks of the values from smallest to largest instead of the actual values themselves. And so when there's ties, that can cause some issues, but we don't need to pay attention to those issues here. So which pair of variables have the strongest negative correlation? That's going to be at the very top of the list. Scanning up, we see that the two variables are the same as the analysis that we did with Pearson's correlation here. Desired weight and the number of body piercings. I think I misspoke. I think we had a different pair for Pearson. But there we go, strongest negative association with desired weight and number of body piercings. Let's just look at that relationship using the plot command. So the command is y_x, say what data frame those things are living in. And in this case, let's treat as our y variable the desired weight of someone and the x variable as the number of body piercings. So adding in where those data points live, we can see, all right, this is what the scatter plot looks like. Should we be using Pearson's correlation to summarize the strength, or should we be using Spearman's rank correlation? Well, like I was saying, we only want to use Pearson's correlation if the point cloud looks to be well described by an ellipse. Basically, the trajectory is linear, there's no heteroscedasticity, and there aren't any extreme outliers. In here, we see a case where that's not really describing the shape of the point cloud here. So what we see is heteroscedasticity. We see that there's a large scatter in the y values when we have low body piercings, but not quite as much scatter over here. We have this outlier that's sticking out like a sore thumb. So we're probably better off actually using Spearman's rank correlation to gauge the strength here, because this point cloud doesn't really resemble an ellipse all that great. So we should use Spearman's rank correlation here, because the point cloud does not really look that elliptical. It is heteroscedastic and has an outlier. Okay, so this is the correct way to look at this association between desired weight and number of body piercings. And we see that's actually a really strong negative association with a Spearman's rank correlation of minus 0.7. And it only goes down to minus 1, so that's pretty big. The p-value of this is much less than 5%, so it's a highly statistically significant association as well. So, all right, what do we do with this? Well, we remember the limitation of this sort of analysis. Even when we do find a strong association, that's never evidence or kind of proof that there's a cause and effect relationship going on. There's obviously not a cause and effect relationship here. You know, if you go into the mall and get another piercing somewhere, that's not going to cause your desired weight to shrink. Like just getting a few more piercings isn't going to make you wish you weighed less. So there must be another explanation for why we see this strong association. Now, it might have just happened by chance alone. That's always possible. But in this case, there could be a lurking variable. If you think about it, it might be that gender is able to explain why we see this association. Why might that be the case? Well, typically, girls tend to have more body piercings than guys. Girls also weigh less than guys on average, and girls, you know, their desired weight is probably less than the desired weight of guys. You know, the standard image of beauty is having a skinny girl. The standard image of beauty is to have a strong, muscular guy. So there would be a pretty large difference in desired weights between the genders. So most likely, we're seeing just the women in the survey over here with large body piercings and small desired weights. The guys, which most often have zero body piercings, are wishing that they weighed quite a bit more. So gender is probably a lurking variable here. Gender is probably a lurking variable. Girls have more piercings and wish they weighed less than their male counterparts here. And that's enough to explain why we see that negative association. All right, question 2 deals with the movie data set. So let's go ahead and load that up with the data command that also lives in package reg class. And what this data set does is it looks at the opening weekend gross of movies and then also the total gross over the course of its run. And the units here are in millions of dollars, so when we see tiny numbers here, that means that, okay, the movie just didn't make all that much. 0.000349 is something like $3,490, something really small. All right, so let's see what we can discuss about the association between these two quantities. If you're Regal, which is based in Knoxville, you'd like to study the relationship between how much money a movie is going to make based on its opening weekend performance. So let's see what we can find out. Let's run the associate command, which does all aspects of the analysis for us. If we're going to predict total, then total's our y variable, weekends are x variable, so y twiddle x. We say what data frame the variables live in, and we're going to leave it as that. We're not going to put in a random number seed. Okay, so there we go. Which measure, Pearson versus Spearman, is appropriate for testing the significance of the relationship? We see it's a very strong relationship going on between weekend and total gross. But we see that, okay, based on the shape of this stream of points, we're better off approaching analysis of this relationship with, once again, Spearman's rank correlation. Why is that? Well, the trajectory of the stream of points is linear, so that's a good sign. But we do see this heteroscedasticity again. We see a small vertical scatter for movies with small weekend grosses, but a much larger vertical scatter when we look at movies with larger weekend grosses. And we have an outlier over here. We're better off approaching this with Spearman's rank correlation. Okay, so Spearman's rank correlation. The point cloud is heteroscedastic, and there are outliers. So it actually doesn't really matter which one we pick, because if you notice, the p-values of both of these measures of strength are essentially 0. We've narrowed it down to somewhere between 0 and 0.007. Both of those options are less than 5%. So regardless of how we approach the relationship, we get a statistically significant result. But Spearman's rank correlation does somewhat of a better job summarizing this strength. And we see how strong this is. It only goes up to +1, and getting something at 0.95 is pretty impressive here. All right, often in business analytics, we run into cases like this, where we have a point cloud that has heteroscedasticity, and we have cases where the distributions of our variables is highly skewed. The distribution of weekend gross we have a lot of movies with small weekend grosses, and it tapers off slowly towards higher amounts. And same thing for total gross as well. A lot of movies with small total grosses and a right-handed skew towards higher values. And very often, this suggests to us that we really shouldn't be analyzing the collected amounts, but instead look at the logarithms instead. So we can redo this associate command and just change the variables that we're actually studying. In this case, let's look at the logarithm base 10 of the total grosses versus the log base 10 of the weekend takes. All right, and when we do this, then the scatter plot changes somewhat. Now the numbers we see here are the exponent to which 10 is raised to get that number. So 1 corresponds to a weekend gross of 10, minus 2 corresponds to a weekend gross of 0.01, etc. here. So same sort of story, we see that the p-values of the relationship still essentially 0, highly statistically significant, but this point cloud looks, a little bit nicer, and really just a little bit nicer. We do see this heteroscedasticity once again, where we see a lot of scatter for movies with log 10 weekends between -1 and 2. Not as much scatter over here, so still probably more appropriate to use Spearman's rank correlation to analyze the relationship. But overall, we see that we have much nicer distributions for the variables themselves here. Okay, so notice how Spearman's rank correlation is the same value as before. Notice that on the original variables, it was 0.9511. Looking at the logs, it's still 0.9511. That's one of the nice things about Spearman's rank correlation. If you square values, if you take the square roots, logarithms, Spearman's rank correlation is going to actually have the same value. Not true for Pearson's correlation. We see that with the original values, it was 0.915, and now with the log values, it's 0.931. So the correlation looks a little bit stronger here. So Pearson's correlation has increased from 0.915 to 0.931. Now, we're really using Spearman's rank correlation to study this, but we see that this point cloud is a little bit more appropriate to approach with Pearson's just because of the, a little bit nicer of a flattened ellipse than what we saw here where we have this fanning outwards. But the numbers don't really change all that much. All right, so there you go. That's activity 3.